All right, so welcome. In today's video, we're going to introduce the definition of convolution and discuss a few of its just basic properties. So the convolution of two functions is, say, two functions of t is another function of t, usually indicated, either f of t, and then you have this sort of star-looking thing, or just f g and then of t. And what it is, it's the integral from 0 to t of f, and we need to introduce some other variable here. Your lecture notes use tau. I am not going to use tau because I think it looks too similar to a t. So this is the Greek letter tau. I'm going to use w. But it's f of w times g of t minus w. And we're taking the integral of that with respect to w. So one sort of thing to note is that, this looks very similar to a multiplication, but it is not multiplication. Okay, so let's just work through a couple examples. So our first one, we have 1 convolved with t. So this is going to be the integral from 0 to t of 1. Normally we would plug in w, but there's nothing really to plug in, so it's still just a 1, times t, but with t replaced with t minus w. So we integrate that, and now remember, you're going to have multiple variables floating around. It's important that when we plug in our bounds, we plug them in for w. So here we have t times t minus t squared over 2, and then minus t times 0 minus 0 squared over 2. So we end up with t squared minus t squared over 2, and so we can get our final answer. The convolution of 1 and t is equal to t squared over 2. Okay, so another really important thing to note again, I think people get confused about this because it sort of looks like a multiplication sign, but 1 convolved with some function is not just that function. In fact, even taking the convolution of 1 with itself, we actually end up with t as opposed to just 1. All right, so let's look at another example. We're taking the convolution of e to the t and e to the negative 3t. So for this first e to the t, we're replacing that t with a w. And for the second one, we're replacing t with t minus w. Okay, so here we're going to sort of note, we're going to rewrite it. And now we're going to note that we can pull out this e to the negative 3t because it's just a constant from the perspective of w. Okay, so we'll note here, right, this is just e to the 4w. So if we take the integral of that, we end up with e to the 4w over 4. And then we're taking that from w equals 0 to w equals t. So we plug both those in, and if we move the e to the negative 3 back inside, we'll see that what we get is e to the t over 4. That's a 1, so minus e to the negative 3t, also over 4. And that's going to be our answer here. Right, so before I sort of continue, I just want to give you guys a couple problems to work through. So compute the following. So for the first one, compute the convolution of t with itself. For the second one, I want you to compute the convolution of e to the at with e to the bt. And yeah, let's actually just leave it there. So take a pause, take a second, and try to compute these. All right. So let's go over what these answers should have looked like. So note, when we write this down, we should be taking the integral from 0 to t of w times t minus w. You should have then ended up with w squared over 2 times t minus w cubed over 3 from w equals 0 to w equals t. And then your answer should have just been t cubed over 6. Right, similarly here, e to the aw, e to the b, t minus w, you could again sort of pull this out, this e to the bt, And then from there, it's pretty straightforward, and you should have gotten as your answer e to the at over a minus b plus e to the bt over b minus a. All right. So before I end the video, I'm just going to denote a couple properties of convolutions. So the first of which is a sort of distributive property. So this follows, right, if I just set up the integral for this first thing, and I split it up, I distribute and I split it up, I can see that I have distributivity. Whoops, and I wrote down dt when it should have been dw. The second, so yeah, this one's called distributive property. This next one is associative property. This one's a bit harder to show, but the crux of it is that it doesn't matter if I have to do 3 convolutions, or really 2 of them. It doesn't matter what order I do them in. The third is the identity property. So remember, the convolution of 1 and a function is not equal to just that function. However, there is a function that does behave like the identity. And that's the delta function. And to sort of see this, remember that if I am integrating, something, and as long as really as long as the point everything's sort of concentrated at is in between A and B. So as long as this C here is in between A and B, then I just get f of C. Yeah, so here, for instance, I could see the integral from 0 to t, right? This is a concentrated sort of at 0. So if I do this, what I end up with is f of t minus 0, which is just f of t. So another way of writing this identity property is the convolution of the delta function with any other function is just that function. And similarly, if I change the order. And the final property, which is a little bit harder to see, is the commutative property. This says that it doesn't matter in what order I take the convolution. I could do f and g, or I could do g and then f. You're going to get the same answer. So to sort of see this, really all we have to do here is a pretty simple u sub. So we set u equal to t minus w. So then du is negative dw, remember, because that's what we're integrating. We can treat that t like a constant. And if I solve this for w, I get w equals t minus u, dw equals negative du. Okay. So if I'm doing this u sub, I also have to change my bounds. I can see that when w is 0, then u equals t. And when w equals t, I get t minus t, or 0. And then remember, if I have a negative out front, I can swap the bounds on the top and bottom. And now we can see this is the convolution of g of t and f of t. But I started, right, with the order the opposite way. All right. So this is not, this commutative property is actually insanely useful sometimes. So let's close with one last example. So I want to compute the convolution of t with t to the 5th. All right, so if I try to do this sort of naively, I get something that doesn't look the best. I would have to expand, you know, a 5th power, which is not fun. But if I use the commutative property, I can just compute t to the 5th with t, and that is much easier to do, because then I don't have to expand anything. So I compute that. I get t to the 6 over 6 times t minus t to the 7th over 7 minus 0 to the 6th. Well, that whole second term is 0, and so I can get that t convolved with t to the 5th is equal to t to the 5th convolved with t. And that whole thing is just going to simplify to t to the 7th over 42. All right, so I will end it there.